Well, thank you. I'm John Corey, machine learning specialist with Xilinx. I cover North America, and I assist customers primarily with the deployments of machine learning models into their target technology. So in this presentation, I'm going to cover Vitis and Vitis AI. We'll just have sort of a brief overview of each of these, and we'll get into a few details on the Vitis AI design flow. We'll look at deployment for both cloud and edge, what targets we have available, and we'll point you to some great resources to get you started with deploying your machine learning models into Xilinx technology. Finally, we'll touch on some other things that we're doing other than CNNs. So we have been very focused in the past on convolutional neural networks, but we have also been researching and developing solutions for other areas. So Vitis is a unified software platform. The goal of Vitis was really to bring Xilinx technology to the masses, to those who are software developers, to those who are data scientists, and to provide a design entry point for designers to take advantage of not only the processing system that we have in a Zynq or Zynq UltraScale Plus, but also to take advantage of the programmable logic. So Vitis allows you to target a platform, whether it be edge, a Zynq UltraScale Plus or Zynq 7000 device, or cloud, which could be an Alveo on-premise deployment or a true cloud deployment. And we provide something called the Xilinx runtime library there, which helps to abstract things. It allows you to manage the transactions between either the processor and programmable logic in a Zynq device, or the host x86 processor and the Alveo accelerator card over PCI Express, so it manages all the memory transactions for you. On top of that, Vitis provides compilers, analyzers, and debuggers. Now, these aren't AI compilers, they're software compilers such as C, C++, and so on. The analyzers are to help you understand the performance of your code running on the target, and the debuggers, of course, are to help you functionally debug your code. Now, on top of that, we have a suite of accelerated libraries. We have the Vitis Vision and Image Processing Library, which I'll touch on in a bit more detail. And we also have the Vitis AI library that you're seeing here. And this will really be the focus of the presentation today. So Vitis AI is really in existence to give you access from the framework to go directly to Xilinx hardware. So it allows you to plug into TensorFlow, Caffe, and PyTorch, as well as Apache TVM. Apache TVM is kind of a parsing framework that allows you to work with all different frameworks, and it also can allow you to deploy layers in software to run on the processing system, as well as to compile for the programmable logic. We also have a suite of Vitis AI models in our model zoo. So we have over 50 models today, including 2D detection, pose estimation, segmentation, and many different variants of each of those types. Those models are supported by the AI library, which allows you to deploy them and test them rapidly. And if you have a custom model that uses similar or the same pre and post processing as these types of models, you can also deploy your custom model very rapidly with the AI library without having to write any software yourself. We also have the Vitis AI Optimizer. The AI Optimizer provides you with the ability to take a model and to optimize it against a specific data set. So this involves removing compute from the model to reduce the latency, to reduce the memory footprint, and to increase the throughput of your model. We have the quantizer and the compiler, and these are really what I would consider the core tools of the Vitis AI development kit. They're required, each step is required to deploy on one of our targets. So the quantizer takes a floating point model and quantizes it to an integer format. Today we support int8 with our DPUs, although we're going to int4, we're going to be providing some solutions around int4 for the Zynq UltraScale Plus family. The AI compiler then takes the output of the quantizer and it compiles it into an executable file. And the profiler helps you to understand the performance, the memory bandwidth of each layer, the time each layer in the model is taking to execute, and can provide some nice graphical depictions of those things. That helps you understand the performance running on the target and where your bottlenecks might be in the system. Again, this is supported by the Xilinx runtime library. Just like with Vitis, this manages memory transactions to and from either the processing system in the Zynq UltraScale Plus and the PL, or from the host x86 processor and the Xilinx Alveo accelerator card. At the heart of this solution is really what we call the DPU, the Deep Learning Processing Unit. And we have a CNN DPU today. We also have LSTM DPUs, and we have other types of DPUs that are in development. There are DPUs that are targeted towards specific tasks, and you can think of this as a soft co-processing IP core that sits in the programmable logic and does the heavy lifting of the neural network compute. Regarding the Vitis libraries, the top here is showing some domain-specific libraries, and the bottom is showing some common libraries that scale across different vertical types of markets. We have over 500 functions in these libraries that have been performance optimized to give you acceleration for those types of tasks. The one I'm going to touch on specifically here is the vision and image processing library, though each library in general makes use of our high-level synthesis tools to take code from C and C++ and to compile it into an accelerator that runs in the programmable logic. Many of these will come with example code to test and deploy and to help you get up and running with it rapidly. This example shows how pre-processing acceleration can be used with the Vitis Vision library. The design here specifically takes video from a 1080p 60 camera source. It goes through a color space conversion and a resizing operation, after which the DPU, the Deep Learning Processing Unit, is used to do face detection on the video stream. The post-processing overlays bounding boxes onto the output video stream, and you can see in the initial example here, we were achieving 13 frames per second. Now, the limiting factor to this actually wasn't the face detection algorithm, the model that was being run on the DPU, but rather it was the color space conversion and resizing that was happening in software up front. So these were being run in OpenCV on the ARM processor. So in order to accelerate these, we used the XF namespace, which is the Vitis Vision library, and we used the UIVY to BGR function, and the XF resize function took the output of that and converted it to the proper format for the DPU. And we were able to boost the performance of this from 13 to 60 frames per second. And you can see these two functions really operated in a streaming fashion. So the output of UIVY to BGR went directly to resize, and the output of that then went to memory for the DPU to operate on it. So really the point of that is that system acceleration and the whole system application is really very important to consider. So not just the performance of the machine learning accelerator and how many frames per second or tops it might have, but what other functions might need to be accelerated, whether it be pre-processing or post-processing. With that, I'd like to talk a little bit about the Vitis AI design flow. So the Vitis AI design flow starts just like any other machine learning design flow. You start off in a framework like TensorFlow, PyTorch, or Caffe. In this case, you would have a data set, of course, and the training and evaluation code. And I think John's walked through this in great detail, showing how you could use TensorFlow or other frameworks to train a model. The output of this process is a trained model checkpoint or frozen protocol buffer of some sort. So that model would be then ingested into the Vitis AI toolkit. Now, the first step that's shown here is the optimizer. Again, remember, the optimizer actually is not a required step. It's only used if you want to increase the performance of your model running on the target. The optimizer takes the floating point model and prunes it, removing unnecessary compute. And the output of that is a pruned floating point model. So we're still in floating point format here. This floating point format model is ingested by the quantizer, which does an intelligent quantization to produce an int8 model that can be ingested by the compiler. The output of the compiler then is determined based on what you're targeting, whether it be Alveo or Zynq. So if you select Alveo for your target, you'll end up with a .x model file, which can be run on your Alveo board. If you target Zynq, you'll end up with a .elf, an executable linked format, that can be run on the DPU in the Zynq UltraScale Plus device. The final step here is hardware and software integration. So hardware integration is not required for many developers. So if you're targeting a pre-built SOM, or if you're targeting a Xilinx development board for a Zynq device, or if you're targeting an Alveo card, many of these are delivered already with board images that have been built. So they have the DPU already integrated with all of the underlying Linux and everything that you need to get up and running. Now, if you're developing a custom piece of hardware, then that would potentially do some hardware development, as well as for Alveo. If you're targeting Alveo and you'd like to do some additional acceleration of other functions, then you may be also doing some hardware development to accelerate those functions in addition to the DPU. The software integration piece could be using Vitis AI libraries, which could be used to deploy rapidly a variety of models, or you could be writing some custom code and using the Vitis AI runtime. The AI runtime interface provides a common set of APIs to deploy models between either Zynq or Alveo. So you can actually deploy virtually the same code on a Zynq as you can on an Alveo to run your model. This slide gives you a little bit of an overview on the Vitis AI optimizer. So the model of interest here is SSD with a VGG backbone. It was trained on a 4-class data set for surveillance. And the blue bar that you see here on the far left is the number of gigaops required by the model to do one inference. So if you send one sample through the model, this is how many gigaops are required to compute the output. The gray bar here is the mean average precision of the model on the data set. So you can see at the initial start here, we achieved 61.5% mean average precision, and the model had 117 gigaops. The first step of pruning here removed over half of the model's compute, and what's not shown here is a retraining step. So there's a fine-tuning that happens here where we recover lost accuracy, and that's where we end up at 63.4% mean average precision. And what you're probably wondering is, well, how did it get better? And the answer is that the initial model here was overfitted to the data set. So there was more compute in the model and than was required for the data set, and it was memorizing the features. So the initial step reduced half the compute, and each iterative step after this, you can see, is reducing the compute by additional amounts. So there are thresholds that you set in the pruning tools that determine how much is going to be removed after each step. And after each step, you're going to do a fine-tuning phase to recover lost accuracy. And you can see that we actually had the same accuracy on the 7th step that we did on the initial model, but we reduced the accuracy in a huge, or reduced the compute required in a huge way here. We continue pruning here, and you can see the accuracy kind of starts to fall off here towards the end. And we ended up at a point here that had about 1% less accuracy than the original model. But the model compute has been reduced by about a factor of 10 times. This results in a speed up when running on the Zynq UltraScale Plus device from 18 frames per second to 103 frames per second for this model. So the necessary 2 steps that you need to take to deploy your model is to quantize and compile it. The quantizer workflow is shown here, and it starts off with the floating point model and a calibration data set. Don't be scared of the calibration data set. This is really nothing special. It's just somewhere between 100 and 1,000 images from your data set. And these should be representative of what the model would see in the real world scenario once it's doing inference. So what the quantizer does is it ingests these 2 pieces. It runs forward passes of the calibration data set through the floating point model to determine the dynamic range. After that first calibration step is done, the quantizer can optionally do a test step. So for this, you would need to have your validation or test data set present with labels so that you could test the accuracy of the quantized model. If the accuracy is good after this step, you can go right to the compiler. If the accuracy is not so good, there's a couple things to look at. First of all, you might go back and look at your model to understand if the architecture of the model lended itself well to quantization. By that I mean, did you use mean value subtraction on your pre-processing? Did you use input normalization, dividing each pixel, for instance, by 256 or 255? And those are good practices, as well as including batch norm layers in your model. You can use the Vitis AI model zoo models as a good reference for what a quantizable model might look like. So the training data set here is required if you want to do fine tuning. This is the second option. So if your model accuracy is bad or not as good as you'd like, and you really want to improve that, but you know that the architecture should be very quantizable, you can run it against this training data set with the quantize fine tune option. And what we're showing here on the top right is the accuracy of a variety of classification networks. You can see the floating point accuracies here for the top one and top five. And then you can see the 8-bit quantized. Now these numbers are actually without any fine tuning. So these are, common models that you'll find in the public domain, Inception v1 through v4, ResNet 50, MobileNet v1. And you can see that for virtually all of them, except for MobileNet v1, we're within 1% accuracy degradation. So we're very close to the initial model accuracy without actually doing any fine tuning. Now with fine tuning, we can achieve much better accuracy for MobileNet v1. And some other models like MobileNet v1 may require a bit of fine-tuning because they use special operators like depthwise convolution, which are a bit more difficult to quantize. The final step there then is to compile the model. So you get the output of the quantizer ingested into the compiler, and the compiler will do the parsing, optimization, scheduling, and code generation, which will result in a .x model or .elf file that can be run on the DPU. So what we just walked through here is this flow on the left. This allows you to go from a framework to a compiled model file that will run on the DPU. The second step for the development flow is to build the hardware. Now, again, I mentioned earlier that this really isn't necessary a lot of the time. So if you're working on a development board like the ZCU102 or ZCU104, or you're targeting an Alveo card, you actually don't need to do this step. If you're targeting custom hardware, however, or you want to accelerate additional things on your Alveo card, then you might want to do this step. So this would basically include incorporating the DPU IP into your design, using maybe C or C++ to develop any other accelerators or RTL, perhaps using some of the accelerated libraries that we have with the Vitis compiler, such as the Vitis Vision library, linking things together and then building the hardware using Vitis. The final step here is to build the software, and we provide you with the Vitis AI runtime APIs, which give you a common unified software environment or software API to deploy models across both Edge, Alveo, and Cloud Alveo devices. So we support C, C++, and Python with these APIs, and we have, of course, support for GCC and G++ with the Vitis tools. We have the AI library, which I haven't talked a lot about, but there's a lot of C and C++ source code included here that can run all of the models in the Xilinx Model Zoo. And you can adapt this code as well to run your own custom models. The built software then will pull in the compiled model ELF file, and we'll run that and deploy it on the DPU and do additional things potentially like display your output and overlay bounding boxes and things like that. So let's talk a little bit about deployment targets. In terms of the Edge, we have the Zynq family that has built-in Cortex ARM processors. The UltraScale Plus device has the quad-core A53 and a dual-core R5, and the Zynq 7000 has a dual-core A9. The Zynq UltraScale Plus family has a subset of devices that include H.264 and 265 codecs that support 4K P60 simultaneous encode and decode of video. And that's ideal for applications that need to stream video over Ethernet or compress video for storage. The ARM Mali 400 GPU is included as well. And that's really a graphics GPU that can do 2D and 3D overlays and send that data over DisplayPort for display. So we have a hardened DisplayPort controller as well as many other high-speed interfaces in the device. Many of these are hardened in the processing subsystem, and many can you build in the programmable logic, virtually anything you want. So that's one of the great things about programmable logic. The cloud and data center side of things have a Alveo family of PCIe cards, and we currently support the U50, the U50 low voltage, the U280, 200, and 250, and we're adding the U25 soon. So you can download the pre-provided DPU configurations directly over the PCIe connection to the board from your host machine. So you don't have to do any hardware development there. Now you can mix that Xilinx DPU again with your own custom logic if you want to do that hardware development flow. So the following will be a little bit more detail on the deep learning processing unit. And you can see here that the Vitis target platform, this is kind of showing where the Vitis target platform might sit with respect to a device. And the block that you're seeing down here is sort of the remaining configurable logic that you have in the device for the DPU. Now the DPU is flexible across different applications. It's a programmable vector processor, and it's optimized for different end targets. It could be optimized for latency or throughput. It could be targeting different types of models like LSTMs, RNNs, or MLPs. And in an Alveo card, of course, you have an AXI interface here, or a PCI Express interface here that goes up to your host CPU. In a Zynq UltraScale Plus type of system, you would have an AXI bus that shares the processor's memory. Now, of course, this is very scalable across all our different platforms. And if you look at the DPUs that we have today, we have a latency-optimized DPU that targets the Alveo U280 and U50, and it's optimized for things like MobileNet. Now, these two cards have high bandwidth memory. The U200 and U250 have DDR4 memory integrated. So the two different DPUs are optimized for different types of memory. And this DPU is optimized for extreme low latency with high resolution, whereas the throughput optimized DPU is targeting more sort of general purpose and high throughput at a medium latency. We also have a throughput optimized DPU for the HBM memory devices, and that's a low cost and high efficiency solution for things like ResNet and Inception. Finally, we have the scalability optimized DPU for the Zynq and Zynq UltraScale Plus. And this DPU scales all the way down to small devices like a Zynq 7020 or a ZU2, and scales up to very large devices like a ZU9. The DPU can be instantiated with up to 4 cores running in parallel, and can support different types of layers and operations based on your user selections. Finally, with the DPU, I want to mention that we have a 4-bit optimized DPU coming for the Zynq and Zynq UltraScale Plus platforms. It uses approximately 45% less memory and matrix compute resources. And this is not out today, but it will be coming hopefully in the next couple of months. You'll be able to get this DPU and to try it out. Really, if you're targeting applications where you can suffer potentially a small accuracy loss, but you really need to get more frames per second or lower latency, this might be a good fit for your application. You can see for segmentation, we achieved close to the original accuracy as well as for classification and for a 3D detection point pillars model. The amount of compute is boosted because now we're using 4-bit operations, and we can make the most out of the device by reducing that bit width. So we go from about 0.69 tops in an Ultra 96 board, which is a ZU3 device, to about 1.23 tops. And for a ZC104, about 2.5 to about 3.7, and the ZC102 about 3.7 to about 7.3. So we almost double the amount of compute that we can get out of a device by using 4-bit. So where do you go to get started with all of this? So Vitis AI is available on GitHub today, and you can clone or download the repository there. The link is right here. And what's included is Docker containers that have the ML frameworks pre-installed with the Vitis AI tools. It does not include the optimizer by default, but you can get an evaluation license for the optimizer by contacting your local FAE or salesperson. There's 2 versions available. There's a CPU version and a GPU version. Obviously, the CPU version doesn't require a GPU card. Now, the reason why you would use a GPU version is because it accelerates the quantization phase. So you might go from 30 minutes with a CPU to do quantization to 1 or 2 minutes to do the same quantization on a GPU. You can also run your training within the Docker environment inside Vitis AI using the GPU approach. You could do that with a CPU as well, but most people don't do training with a CPU, as John mentioned earlier. Either download the pre-built Docker images, of course, so we provide the image to you for the CPU. The GPU image you would need to build yourself, but we have all of the scripts and recipes to do that, as well as with instructions to do that in the GitHub repository. We also have the Vitis AI Model Zoo, and this is one of the first places to go to check out what models we have today supported, and those have the weights as well as the floating point and quantized versions. And they're in different formats depending on the model. So we have TensorFlow, PyTorch, Caffe, and DarkNet models in here. Some of them may be the same model that's been trained in both frameworks and have checkpoints for both frameworks. And some versions here may be pruned against a certain data set to show you how pruning can be advantageous for deploying that model. One of the great things about the Model Zoo is that we benchmark these models against our different hardware targets. So we have the performance listed for all the different Xilinx targets like the U50LV, the U50, the ZCU102, the U280, the U250. And what you'd see is every model listed out with the frequency that the system was running at, the end-to-end throughput, and the latency for that model. The naming convention is very useful as well. It tells you what framework the model was trained in, what the model name is, what the data set was that it was trained on, the input image size, and the number of gigaops in the model. All of these have code included for testing, demo, and evaluation, which is also very useful for getting up and running with that model. We also have the Vitis AI tutorials. These are written by individuals like myself and Mark Harvey, as well as Jim Heaton and many others at Xilinx who have basically run end-to-end flows showing you how to set up your training environment to train the model from scratch, to quantize and compile the model, and then have already written the code to deploy that model on the Xilinx target. So this is a really great repository of examples to go check out. See if there's one that's similar to an application that you have, and then go and run with that. It's a really good way to get started. There are also Vitis AI training courses. So there's a full training course that's online or instructor-led, includes 16 hours of training with labs, and covers the entire Vitis AI design flow. So finally, I want to wrap up with the fact that we're not just focused on CNNs. We've actually just released a Vitis data analytics library in 2020.1. Now this includes other types of machine learning algorithms such as decision trees, random forest, logistic regression, support vector machines, naive Bayes, and k-means clustering. We've also been working with the Deep Speech 2 algorithm for some time now. We had a version of this that ran as a demo on Alveo cards, and now we've ported this to run on the Zynq UltraScale Plus. We have a software-only and hardware-accelerated version of it available, and the conversion time is actually faster than speech duration time, so it gives you real-time speech-to-text capability. We're coming out with a public recurrent neural network processing engine, a DPU specifically for RNNs, toward the end of this year. So in summary, we provide today an easy path to go forward with machine learning inference from your framework directly to a DPU, whether it be an on-premise, a cloud, or an edge device like a Zynq or Zynq UltraScale Plus. We provide you with the capability to compress your model using pruning and quantization. We have the hardware accelerators that are very scalable to go to the low-end Zynq UltraScale or Zynq 7000 devices and scale up to the high-end Alveo cards. We have a software stack, APIs, tutorials, examples. There's a lot of great information out there to get started today. So programmable logic, of course, I always want to mention here that it provides a perfect solution to the whole application. It's not just about machine learning. Applications are about a lot of other things and include a lot of other things like pre-processing, post-processing, and other types of things, flexible interfaces, platform designs. And really programmable logic gives you a great fit to address a variety of needs. It's very easy to scale up and down between the edge and the cloud with these unified APIs. And we also provide you, of course, with support for that chip-down design that fits your needs perfectly. So thanks for your time, and that's all I had today.